So Dr. Stephen Levin is the project scientist for Juno and the lead scientist for the Goldstone Apple Valley Radio Telescope project. He's been at the Jet Propulsion Laboratory for over 25 years, working on topics such as the search for extraterrestrial intelligence, measurements of the cosmic microwave background radiation, modeling radio emissions from the Jovian radiation belts, and measurements of magnetic fields in cold molecular clouds to improve our understanding of star formation. He is also passionate about education, frequently giving science talks to students and the public, and is currently president of the Culver City Board of Education, and a member of the Los Angeles Astronomical Society. So I'd like to welcome Dr. Stephen Levin.
Hi, everybody. So if we're ready, I'm going to just go right into the presentation here, right? So let's see if I can figure this out. So share screen. And should all be seeing my desktop here while I bring up a presentation. Okay, can you both hear me and see the screen?
We can hear you and see the screen.
Yep, we're good to go.
Okay, so I'll run through this. I'll try to be really quick to save time for questions, and you guys can ask me anything you want because I'm really good at saying I don't know. All right, well, let's start this way. So that's straight off our website, and it's a nice dramatic way of saying that it's really important to try to understand Jupiter, not just for its own sake, but for what it can tell us about the history of the solar system. And the reason why Jupiter is so important, there's lots of reasons, but if I break it down into a few of the main ones, first of all, it's the largest planet, but not just the largest planet as in, you know, it's a little bigger than the others and Saturn comes close or whatever. The way to think about this is because Jupiter is 300 times the mass of the Earth, because it's more than twice the mass of all the other planets combined. If you were coming on our solar system from far away and you looked at the solar system and you said, what do I see? And you saw the sun and you said, that's it, that's everything. You'd be 99.5% right, because 99.5% of the mass is in the sun. But if you kept looking and you looked really hard and you said, all right, I find this little speck there, and that's Jupiter, now I've got it, now I've got everything, you'd be 2/3 right, because more than 2/3 of the remaining mass is in Jupiter. So in a very real sense, the rest of the solar system is the leftovers. Jupiter formed from the leftovers of the sun, and the other planets formed from the leftovers of Jupiter. It almost certainly formed first. We know that its composition is in some ways very like the sun, but as you'll hear later, there's some significant differences that we're trying to understand. And then on top of that, not just because it's big and because it will have influenced the formation of the others by its gravity and by its sucking up the material that could otherwise have formed other planets, but also because Jupiter is important, because understanding Jupiter can teach us a lot about the history of the solar system in a way that a planet like the Earth can't. If you look at the Earth today, part of what we see is determined by large bodies that have hit the Earth. You know, the moon was formed when a Mars-sized object collided with the Earth and completely melted it. the weather on the planet has weathered the surface, but also the composition of the planet is determined by not just when it originally formed, but whatever's happened since. Jupiter is so big that most of those effects are probably not important. You know, a decade or so back, I guess it's more like 2 decades back, a comet impacted Jupiter. Very impressive. You know, a lot of things went into studying it. People from all over the world turned their telescopes at it, made a big splash, you know, marks on the surface of the atmosphere and all of that. And in a few weeks, it was gone, and that was it. And Jupiter was essentially unchanged. If an object like that had hit the Earth, the consequences would have been much more dramatic. So another reason why Jupiter is important is that the history is still there if we can find it. So that's the good news. So, of course, we're going to go find it. The Juno mission is just a few facts here about it. It's a solar-powered spacecraft. It's now the furthest object from the sun that's been powered by the sun, so the farthest we've ever taken solar panels. We have a bunch of science instruments that I'll talk about. It's a spinner, so it basically just spins like a top, doesn't need gyroscopes or anything, keeps it simple. We've been traveling to Jupiter for almost 5 years now, and it's finally going to arrive on the 4th of July. It'll spend almost 1.5 years at Jupiter, and I'll talk about that a little bit more. I'll talk about the science objectives, so I won't use this slide to do it, but I will point out that our project has a principal investigator. And if you know how NASA works, there's basically 2 ways of doing projects. The smaller ones tend to be principal investigator projects where there's one person at the top who's responsible for the whole thing, and they organize and delegate authority down. And the larger projects tend to be organized by committee, essentially. Well, at the time Juno was selected, it was the largest project NASA had ever done with a principal investigator. And I think that actually worked out spectacularly well. Scott's been a really good principal investigator, and we've been able to make decisions quickly because he's got the authority to just say, do it this way. He selected a team as opposed to having the committee select a team. So we selected a team that works really well together, delegates a lot of the authority to JPL to manage it, but he's actively involved, and the science team is actively involved, and it's run by the scientists, not by the managers. And of course, there's a project scientist, me, to represent the interests of science on a day-to-day basis here at JPL, because Scott's based in Texas. All right, so that's probably more than you care about the management structure anyway. Let's talk just a little bit about how you get a spacecraft to Jupiter. So we started by launching it without enough energy to get to Jupiter. And that's because we don't have a rocket that big, or at least we didn't have money for a rocket that big. And what we did, is launch it on an orbit of the sun that gets it out past the orbit of Mars, and then fire the main engine on the spacecraft to aim, come all the way back to the Earth, and use a gravity assist from the Earth. So come in behind the Earth, and the Earth's gravity speeds us up, changes direction, and gets us headed on our way. And so after that Earth flyby in October of 2013, then we had enough energy to get all the way out to Jupiter. We've been basically coasting ever since, and we arrive at Jupiter on the 4th of July. Now, it says 5th of July because we usually use universal time as the way to count those things. And in universal time, it'll be early in the morning on the 5th of July. But it's going to be evening on the 4th of July here in California. So fireworks at Jupiter, fireworks here. There's no way we were going to pass that up. So everybody is calling it 4th of July. All right. A little bit more about why Juno and why it's important to study Jupiter. So even though Jupiter is the largest planet in the solar system, and even though we've been studying it for literally hundreds of years, right? It's one of the very first things anybody ever looked at in the sky using a telescope. Nonetheless, most of what we know about Jupiter is really the clouds at the very top of its atmosphere. It's this enormous gas giant, mostly hydrogen and helium. We can't see beneath the clouds. Most of what we know about it is those jet streams and the Great Red Spot and the storms and all the fascinating atmospheric dynamics. We think down in the center, there ought to be a dense core, something like 3 to 20 times the mass of the Earth. We have no direct evidence that it's even there. It's got an enormous magnetic field, the strongest in the solar system of any of the planets. We think that's generated by an ocean of liquid metallic hydrogen formed by the enormous pressure of Jupiter. When you get about a third of the way into the planet, you're up to a pressure something like 2 million times the pressure here on the Earth. And that's strong enough so that not only do you squeeze the hydrogen down and make it a liquid, but it's squeezed so much the electrons are squeezed right off the atoms, and it generates, it conducts electricity. It's a metal, so you have liquid metallic hydrogen. Well, we think it's the swirling motion of that liquid metallic hydrogen that generates the magnetic field. But of course, nobody's ever sampled that. Nobody's ever held liquid metallic hydrogen in their hand and proven it exists. And we don't quite understand the details of how a planetary dynamo works. If you want to understand how do planets make magnetic fields, you might think, well, crawl around on the Earth and measure the magnetic field everywhere here and figure out how the Earth's dynamo works. But the problem with that is the Earth has this solid crust with magnetic material in it. So when you measure the magnetic field on the surface of the Earth, you're not measuring the magnetic field coming from the core in the middle. You're measuring the magnetic field coming from the core plus the effects of whatever magnetic materials are between you and the dynamo. On Jupiter, that's not a problem because what's between you and the dynamo is non-magnetic material. So if we can map the magnetic field of Jupiter, we can really study a planetary dynamo in a way that we can't do on the Earth. We have lots of questions about Jupiter that we hope to answer with Juno. I'm not going to run through them all off this slide. You can read it and pick your favorite thing, or we can talk about them as soon as I get rushed through the end of these slides so we can do questions. I'll tell you just a little bit more about the interior. It's hotter on the inside than the outside, and that's basically because it's still cooling off 4.5 billion years after it formed. So the heat of formation, all that material falling in and making the giant planet under the influence of gravity, you're turning kinetic energy, moving stuff, falling in gravity, into heat as it smacks together and heats things up. That heat hasn't escaped yet because the planet is so big. We're going to use that fact with our measurements, as you'll hear in a few minutes, because that means the inside's hotter than the outside, and the atmosphere cools in a fairly predictable way based on its composition. Okay, so we want to understand that composition of the planet, and we want to understand the interior structure. We see these belts and zones and storms and motions in the upper atmosphere, the weather. We don't know how deep any of that stuff goes. You see jet streams, the belts and zones, moving at hundreds of miles an hour in opposite directions. You see a storm twice as big as the entire Earth. But we don't know whether those things stretch down for 10 miles or 1,000 miles. In order to understand that, we need to know how the heat leaks out and how the atmospheric dynamics work. In order to understand the interior, we need to know what's that structure look like? How deep do you have to go before you reach the metallic hydrogen level? Is there a core down in the center? How does the interior move, as well as how is it structured? So those are things we're going to try to study with Juno. Another key puzzle came from when the Galileo spacecraft went to Jupiter and dropped a probe into the planet. So with Galileo, we dropped a probe into Jupiter. It was designed to reach at least 20 bars, 20 times the pressure here on the Earth, which is skin deep for the planet, but we hoped that would be below the weather, down below the clouds and so forth. And it in fact reached to 22 bars, so it did its job. It measured the composition, but we found something really interesting. We found, if you look at this chart, that if you take the heavier elements, so look at the argon, krypton, xenon, carbon, nitrogen, sulfur that are shown there, and you take the ratio of each element to hydrogen and compare that with the equivalent ratio in the sun, that it was enriched on Jupiter. There was more of the heavier stuff than you find in the sun. Well, if Jupiter formed from the same initial cloud of gas and dust that made the sun, as sort of the leftovers from the sun, and if it formed in about the same way, just collapsing gravitationally, you'd expect about the same composition. So this was a puzzle, and it was also a puzzle that they were all at about the same level of enrichment. Why should carbon, even if there's some chemistry going on or some complicated process where heavier things get pulled in more than lighter things, carbon and nitrogen and sulfur and argon, they all have different masses. Why were they all at roughly the same enrichment? And then the kicker here that was really surprising is the Galileo probe found almost no water. Now, oxygen should be the third most abundant element. It's the third most abundant element in the solar system. It should be present in the form of water, and yet we found practically none. So this was a big puzzle 20 years ago. And the conclusion that most people reached was that we did not get below the weather layer, and we happened to go into a dry spot. We went into a hot spot on Jupiter where the Galileo probe was about the right latitude to do that. And we simply didn't measure the global water abundance. We measured it in one spot, and it happened to be the Sahara Desert of Jupiter. So that's the leading theory to explain that, but it still leaves us with a question of why the other elements are enriched. And the leading theory for that is that perhaps Jupiter formed from cold planetesimals, icy planetesimals. So asteroid-sized objects perhaps, or maybe a little bigger or smaller, that collided together and stuck. And when they got big enough, then they had enough gravity to pull in the gases, the hydrogen and helium. So that would explain the enrichment. And you could try to explain the enrichment of everything being all about the same if you said that the heavier elements were trapped in this ice, and the ice was so cold that it brought in the same amount of everything because anything that touched it basically stuck to it. But that makes a prediction about how much water we'll find on Jupiter. Because if those icy planetesimals form the planet, then first of all, water should be enriched. We should find water at least at that 3-to-1 enrichment level that we're seeing the other stuff at. And if the water had to carry the stuff in with it, and it wasn't super cold, really far from the sun when it formed, if it formed closer where Jupiter is now, it wouldn't be able to carry as much of the heavier stuff with it. So there must be more water in order to explain that. So the ratio of water to hydrogen should be higher if it formed warm. So that's the plot you're looking at now with the two different yellow arrows to show our guesses as to what the theories predict for how much water there should be. And then, of course, if that original measurement really was right, and it wasn't just a hot spot, but it was the actual global water abundance of Jupiter, we have to throw all the theories out. We don't have an explanation of why the water would be that low. Lots of people are trying to come up with things. I'm sure if that's what we measure, the theorists will predict that after the fact. But in general, the leading opinion among all the theorists is we're going to find more water than that. All right. So how are we going to do that? Well, first of all, the science objectives, as I started to say, are find the abundance of the water. The global water abundance is probably the single most important number we're going to measure. Measure the mass of the core, or at least place an upper limit on it if it turns out to be really small. Those both help us figure out how the planet formed, and it's, in fact, the combination of those that's the most powerful. Try to understand the interior structure and how the material moves inside the planet. And we're going to do that by mapping its gravitational and magnetic fields, because gravity comes from the entire planet, and the magnetic field comes from deep inside. Study the atmosphere. Look at the variations in the composition, but also the temperature and the clouds, and the dynamics. In the deep atmosphere, we want to understand how deep do those storms go, and how are they driven, and how do those belts and zones work, and what's happening with the Great Red Spot, and how deep are its roots. So trying to understand the deep atmosphere is an important part of the mission. And then finally, as you'll see, we'll be in a great position to measure the magnetosphere. So this enormous magnetic field of Jupiter traps high energy charged particles, and it sweeps around as the planet rotates. And there are aurora in the north and south, so northern lights and southern lights on the planet that are the largest in the solar system. And we have some ideas about what drives them and how they form, but we don't understand that in any kind of detail because it's really hard when you can't see them, and spacecraft haven't gone over the poles of Jupiter before. So we will understand that as well, because if you look in the upper right-hand corner here, can you guys see the arrow that I'm pointing with?
Yeah, we can see it.
Okay, so if you look in this upper right-hand corner, the way our orbit is going to work is we're going to come in over the pole of Jupiter, cross very, very close to the planet, and then spend 2 weeks out far from the planet, and then do it again every 2 weeks for about a year and a half. And there's a lot of reasons for doing that, but one of them is Jupiter is surrounded by these high-energy radiation belts, shown here with the colors. And what other spacecraft that have come by the Jovian system have done is stay near the equator, but stay way out here outside the radiation belts. Well, we're either braver or dumber. What we're doing with our spacecraft is we're going to come over the top of the radiation belts. They're kind of shaped like a donut around the planet, come very close to the planet and cut down in between the radiation belts and the planet very quickly, and then out the other side. What that lets us do is get really close to the planet so that we can study its gravity by how fast the spacecraft falls, and its magnetic field by measuring the magnetic field very close to the planet. And it also lets us spend very little time in the radiation belts because the spacecraft is moving really fast when it's close to the planet, and we'll spend most of our time out here. So we sweep past the planet in a couple hours in a perijove pass, collect all our data during that time of, say, plus or minus 3 hours around the planet, and then have 2 weeks to send all the data back to Earth and do it again. And over the course of time, because Jupiter's not a perfect sphere, our orbit will gradually move down this way. What's called the line of Apsides will change. And because the planet's rotating very fast, it's actually rotating every 10 hours. So think about that, right? 300 times the mass of the Earth and rotating more than twice as fast. But that fast rotation rate means that if we take our 2-week orbit and make very small adjustments to it, we can pick any longitude we want. The planet will spin around a bunch of times, and we just choose the timing so that each time we go by, we get a new fresh longitude on the planet. So we can make a map. So we'll map its gravity and we'll map its magnetic field. We'll also use a microwave radiometer because microwaves can see through the clouds. And remember, Jupiter's hotter on the inside than the outside, so it glows from the inside. Everything glows in the microwave. If you heat it up hotter, you see more light in the infrared, or if you get still hotter, you can make it glow in visible light. But things even pretty close to absolute zero are still glowing reasonably well in the microwave. So Jupiter is over 1,000 Kelvin down in the inside, in the lower part of the atmosphere where we can see with the microwaves, sort of depicted by this shell here. That's about how deep we can see with the microwave receivers. And the 6 different channels see 6 different depths, so they can measure how the atmosphere, the temperature variation in the atmosphere from inside to outside, which will tell us about the water content. So we're going to get the water with the microwave radiometer, which goes to the origin, tells us about the origin of the planet. We're going to measure the magnetic field, which tells us about the interior and helps with the core and helps us learn about the origin. We're going to use gravity to understand about that core down in the middle. We're going to study the interior with all 3 of those instruments. We're also going to study the atmosphere and use the visible camera and the infrared camera as well that can see the surface, the clouds at the top. But the microwave receiver looks deep inside. The gravity is affected by those belts and zones that are moving, so we can measure all of that. And then we have a suite of instruments that are going to measure the fields and particles that hit the spacecraft, so the high energy particles in those radiation belts, and look at the aurora over the poles of Jupiter as we fly over the pole. Because remember, it's a polar orbit. We'll be getting the first look at the North Pole and the South Pole of Jupiter. All right, I won't take that long on all the slides or we'll run out of time. Here's a little bit about what the spacecraft looks like. It spins like a giant propeller. It's got a high gain antenna that communicates with the Earth, and that's how we measure the speed of the spacecraft. By the way, the frequency is shifted. When you move something and transmit a signal from it, the frequency gets shifted by the motion relative to the observer. So if you look at it from the Earth, you can measure how fast it's moving towards or away from the Earth with incredible precision by measuring the frequency of the radio signal. So we stay in radio contact with the Earth. That tells us the speed, because gravity is what's making it fall around the planet. That tells us the gravity. Then all the other instruments, they look out the side of this giant spinning propeller, and each one sweeps a great circle around the sky. So if Jupiter's over there, every instrument gets its turn to look at Jupiter. So the radio receivers and the infrared camera, which is mounted underneath the spacecraft but still looking out to the side, and the visible light camera and the ultraviolet camera, they all look off to the side and they just sweep over the planet. So we don't have to do any special aiming. The instruments just, everybody gets their turn, and the spacecraft rotates a couple of times a minute. Then all these instruments measure what hit the spacecraft, high energy particles and low energy particles. and plasma waves. And the magnetometer measures the magnetic field from way out here, as far from the spacecraft as we can get it, because we want to measure the magnetic field of the planet, not the magnetic field of the spacecraft. For the same reason, we have two magnetometers, so that one is a little bit closer to the spacecraft than the other. And that way, if we see a difference between what this one measures and what this one measures, we'll know what's coming from the spacecraft, not coming from the planet, so we can correct for it. This gives you a sense of scale, and of course, enormous solar panels, because Jupiter is 5 times further from the sun than the Earth is, so you get 1/25 the power. Nonetheless, it's enough power for us. Somewhere in the neighborhood of 500 watts is enough to run the entire spacecraft. And that means we can use solar power and don't have to have the added complexity of nuclear power on our spacecraft. Okay, the microwave radiometer experiment. This is an example of one of the radio antennas that's mounted on the side of the spacecraft. It's a patch array. I won't go into any detail about how that works unless somebody asks me a question later, but I will point out that it's really pretty. And we also have 5 smaller antennas. That's the lowest frequency, the largest wavelength. We have 5 smaller ones mounted on a plate. So we have one looking off to the side and 5 other channels looking off at that side. And then most of the other instruments look off in that direction. And as you can see from the little diagram, as the spacecraft comes past the planet and it's spinning, if you pick a point on the planet, you see it from here, and then from here, and then from here, and then from here, and so forth along the track of the trajectory. Every time the spacecraft spins, it's moved a little, so any given spot that we see on the planet, we see from a whole range of angles. So now I'm looking at that spot on the atmosphere from a whole range of angles and from 6 different frequencies, each of which penetrates a different depth into the atmosphere. So it's kind of like doing a CAT scan of the Jovian atmosphere, and it lets me determine what's called the lapse rate, which is the change in temperature from inside to outside, and the opacity, how much the atmosphere absorbs the microwaves. And what dominates that absorption? Well, water does. So if I want to know how much water there is, by understanding how deeply I can see and how the temperature is varying with depth, I put those two things together and I can understand how much water there must be in the atmosphere, which, remember, is the one number that we think of as the most important thing we're going to measure. We'll measure lots of stuff, but that's one of them. We come so close to the planet that we can see, when we're really close at perijove, the spot that the spacecraft, the antenna can see on the planet is very small. So that's an example of our spatial resolution. And these are just what's called footprints. Each time we spin around, we see another little spot on the planet. This is just the ones looking straight down. We also, of course, at different timing in the spin, see, say, that spot from when the spacecraft's over here, so see it at an angle. This, which used to be a movie, but I guess is just a picture at the moment, this is what Jupiter looks like from the Earth as seen in the radio, and it tells you why you can't do that measurement from the Earth. Even if I had a big enough radio telescope to get really good spatial resolution on the planet, I'd be seeing the high-energy electrons in those radiation belts rather than the planet. So spacecraft doesn't have to worry about that as much, because instead of a bright light shining in our eyes in the radio, the way it is from the Earth, it's a bright light shining over our shoulder in the radio for the spacecraft, because it's in between the radiation belts and the planet. And this just illustrates the idea of seeing through the depth and points out the extra advantage that there's clouds as well, and the height of those clouds tells you something about the water abundance also. And of course, they change the opacity, so that's another thing we'll see, is where the clouds are. All right, mapping Jupiter's gravity. That's Doppler measurement. You're basically measuring how fast the spacecraft falls. And I just want to point out that with a rapidly rotating planet, it stretches at the equator, and how much it stretches depends on whether there's a core down in the middle, because the dense stuff won't stretch the same way as the less dense stuff on the outside. So we measure the gravity. Effectively, we're measuring the interior. And then those belts and zones on Jupiter, they move counter rotation in every other one. So if they're deep, then the way they bulge out from the planet will be different than if they're shallow. And gravity will let us tell the difference. So if we want to know how deep those belts and zones go, we can learn that both from the gravity and from the microwave experiment. And this illustrates the map that I was talking about. Measure the magnetic field. If it's generated by this dynamo region way down inside of liquid metallic hydrogen, the magnetic field that it generates comes all the way out to the surface. If you measure it on the entire map, then you're effectively measuring the source of the magnetic field, the motions of that liquid metallic hydrogen. And of course, if there's a core in the middle of it, it'll move differently than it will if there's no core. If it's a larger metallic hydrogen region, you'll get a different magnetic field than if it's a smaller magnetic hydrogen region. So in the rotating plane, rotating coordinate frame of the planet, where we take into account Jupiter's rotation and we use the fact that we're adjusting the timing each time, we get these orbits making a net around the planet, and we'll measure the magnetic field all along every one of these lines. Finally, if I can make it do it, there we go. This is the magnetospheric experiment. So here, the main thing we're looking at is the Aurora. This is a picture from Hubble Space Telescope in the ultraviolet of Jupiter's North Pole. And you can see we're seeing it at a very shallow angle because that's the best you can do as seen from the Earth. But it's got this complicated structure where electrons are streaming down the magnetic field line, smacking into the planet and making the atmosphere glow. We want to understand the mechanism that causes that. We think it has to do with where the magnetic field far from the planet has to change from rotating with the planet as it spins around to matching up with the magnetic field stretching out from the sun. If you follow those field lines all the way back, that may be the source that's causing these things to light up. In any event, there's got to be a current, there's got to be electrons coming up and or coming down and coming back up, or protons to balance the charge. And whatever's hitting this upper atmosphere and making it glow should be visible both when it hits our spacecraft, as we cross by, as our orbit passes the magnetic field lines that are carrying it, and as seen remotely with the ultraviolet camera and the infrared camera that look at the planet. So we're in a perfect orbit to study the magnetosphere, because studying the magnetosphere is about studying all the particles on different magnetic field lines, and we cross all of the magnetic field lines because we come over the pole and come back out. So any one of these field lines crosses our orbit somewhere. All right, that's the thumbnail sketch of the mission. I will mention just a couple other things really quickly. One of them is Juno Cam, our visible camera, is there not to do science, but to do outreach and education. It's no doubt we will get some science done with it, but it's primarily there for you guys and for the general public to help us plan which images to take, help us analyze the data when it comes in, turn the raw data into pictures, do the planning to figure out which are the possible places. Everything about the science we do with JunoCam is going to be done in public. So if you go to our website, which is missionjuno.swri.edu, there's a section on JunoCam, and there's a place where you can look at the pictures of Jupiter or upload pictures of Jupiter if you have good images that can be used for planning purposes. Say, I think we should observe this spot with JunoCam, start a discussion about it, argue with people about the value of the science from there, convince the general public who are seeing that website to vote for your hotspot or whatever it is, and we will take that into account when choosing which observations to do with JunoCam, because it's limited by how many pictures we can take. And then the raw data that we produce will be put out for the public to process and turn into images. So all of that is basically open to the public, and if one of the scientists on our team wants to take an image of a particular spot on Jupiter, he's going to do, or she's going to do, exactly the same thing you would. They're going to go to the website, they're going to argue for this is why we should take this spot, take an image of this spot, and they're going to try and get everybody to vote for it. It's really dominated by what the public wants to do. The other extra thing I wanted to mention is the GAVRT project, which is Goldstone Apple Valley Radio Telescope. And that's a project where school kids use a large radio telescope to learn about science by doing real science. So they do real astronomy with the radio telescope, and we have partnered with GAVRT to do observations of Jupiter, so that when our spacecraft is at Jupiter, and taking measurements of the planet in the radio, the students here on the Earth are using a radio telescope to take observations of Jupiter in the radio and give us context. Now, we'll get better measurements with the spacecraft because we're close up, but we're only going to get measurements every 2 weeks when we pass by, and we're only going to be at Jupiter for a year and a half. The students have been taking data for decades and will continue taking data after we're at Jupiter, and they can observe more or less anytime Jupiter's visible because there are students all over the world doing this, so it's class time somewhere. And if you've got kids or you know a teacher who wants to get involved, they can get involved with the Gabbard project and help us out on the Juno project and do other radio astronomy. So I just wanted to put in the plug for that. There's links for various websites and stuff where you can learn more about it. NASA's Eyes on the Solar System, you probably know about that already. There's a special Juno module. And of course, because we're arriving at Jupiter on the 4th of July, we're gearing up for that. There'll be a 4th of July event. It'll be on NASA TV, and you'll get to watch as hopefully the spacecraft fires the main engine when it's supposed to and goes into orbit. That's the end of the prepared stuff. I would love to spend time answering questions, and it looks like we've got a good 15 or 20 minutes left. So hopefully somebody out there, has something they want to talk about.
All right. So maybe if you want to stop sharing your screen, and that way we can get back to seeing you, that would be great.
Sounds like a plan.
Yeah.
Does that work?
So we've got a couple of questions here. And so the first one that we've got is Skip asks, and this might be one that we have a few materials on the website, but sometimes it's a mystery where to get some of these materials. Where can we get Juno stuff, like bookmarks, stickers, posters, things like that they could use with their outreach? Do you have a good source that we could distribute, where to get that to people?
Yeah, so, it's NASA JPL, so we produce all that kind of stuff, and there's a whole machine here. Your best bet, I think, is to go to the NASA website. So, www.nasa.gov/Juno, and that was one of the links, I think, that was just shown a minute ago. And contact us that way. There's a contact button or something on the website, or Juno's on Facebook. You can look for Mission Juno on Facebook and just say, how do I get stuff, Juno stickers or whatever, and one of the outreach people will contact you. I'm reluctant to say just contact me and I'll give you stuff, because if I get flooded, I won't have time.
We would definitely want to shield you from that, and so.
I think you were in contact with Courtney O'Connor, our outreach person, and I'm sure she can help directly.
Okay.
And folks, we'll see if we can get some up on the Night Sky Network website as part of the outreach handout. All the active astronomy clubs, if you've been logging events, you're able to request posters and lithographs and things from NASA. So we'll try and get some of the Juno stuff up there.
Okay, we've got another question from John, who asks, will Juno be making any observations of Jupiter's rings and moons?
So the answer is yes and no. The short answer is the main thing we're going to do about the moons is avoid them. And that's because we have a planetary protection requirement that we have to avoid the possibility of contaminating Europa. Europa is one of Jupiter's moons. It's got a liquid water ocean underneath the ice. There are lots of people excited and interested in looking for life on Europa. There are plans coming together for a mission to Europa. You would hate 20, 30, 40, 50 years from now to get to Europa, dig beneath that ice, sample the water ocean, find life, and then have to say, but I don't know if it's life from Europa or contamination from Juno 50 years ago. So we have to show that we're not going to contaminate Europa. And the easiest way to do that is to dispose of the spacecraft by burning it up in Jupiter's atmosphere. But if we took an orbit that went close to the moons, and something went wrong with our spacecraft, we'd be in much greater jeopardy of impacting Europa than the orbit that we're in, where we try to avoid all the moons so that they don't perturb the orbit of the spacecraft. And even if we lose control, the spacecraft is still far more likely to hit Jupiter than one of the moons. So we only take pictures of the moons from a distance. Most of the things we're set up to measure aren't very effective at that great distance because we're designed to do measurements from really close to Jupiter. But we might get some interesting things. You know, people are ingenious about that sort of stuff, and even though we're at a great distance, we'll try to get something on the moons. The rings of Jupiter are another story. Now, as most of you probably know, Jupiter has rings that are nowhere near as spectacular as Saturn, but it does have dust rings that surround the planet. And they're not that well known because they're hard to see and because you don't like to fly your spacecraft through the ring and potentially get it destroyed. We, however, are flying very close to the planet, right through the ring plane, but closer to the planet than we think the rings go. So we ought to have a good view of the rings looking sideways away from Jupiter along the ring plane. We have cameras that are not designed for that purpose, but nonetheless might be able to do something useful, and we will give it a shot and let you know what we find out.
Okay, here's a question. Is the reason Juno is able to use solar power due to the size of the panel? And all the Dawn use larger panels than Juno? Or does Juno use cells that are more efficient previously on other missions?
So we, of course, picked the most efficient solar cells we could within reason and budget, and taking into account that they have to fly into space. But we wound up needing really big solar panels. And the key really is that we have a relatively low power spacecraft. We run the whole thing on a few hundred watts. And that's because we didn't have any instruments that demanded tons of power. We don't have a radar on board. We don't have gyroscopes to move the whole spacecraft around and do pointing, where it's just a spinner. And the set of instruments that we have turn out to be instruments that can run on low power. So we did that partly by design and partly by luck. We chose the instruments based on what we wanted to measure. We looked at, can we do solar? We said, hey, we can make this work. And then in designing the whole spacecraft, you have a trade space where you decide how many watts do I need? How much mass can I afford? How much power can I generate? And of course, how much time and money do I have? And you're constantly making trades among those of, I can save a little money here, but it costs me power, or I can save some pounds over there, but it'll make things hotter, and or make things colder, and I'll need heaters or whatever. So once we knew we were going to do solar power, we made some trades to keep the power low. But what enabled it was we have relatively low power instruments, and our orbit stays in the sunshine the whole time.
Okay, so here's a question that seems related to that, and they've been reading that 9 times solar means that Jupiter formed as an orbit, but 2 to 3 times solar implies Jupiter moving further out. What's the difference?
So, so far that didn't sound like a question, but
I think the question was, oh, go ahead.
Go ahead.
The question, I think, was why the difference?
Okay.
Why would it be that way?
So the story is a little more complicated than that, but as a basic way to think about it, imagine a chunk of ice that's really far from the sun and extremely cold, and it gets hit by a carbon molecule or a nitrogen molecule. Basically, whatever hits it is going to stick. And it's just going to scoop up material around it, and it can trap it within the ice. And if it's really cold, it will more or less not care what it was that hit it. Whatever hits it is going to stick, and it will collect them all in about the same ratio and pretty much collect a large amount of it. If that's the type of particle or block of ice that collided together with lots of other similar blocks of ice and made Jupiter, then it will carry with it a whole bunch of those heavier elements. Now imagine the same block of ice, but it's much closer to the sun. It's still ice. It's not so warm that it melts, but it's a lot warmer. It's in the orbit of Jupiter instead of maybe 5 times further away from the sun. Now, it doesn't hold as much of those other elements because sometimes they escape. It's warm enough that some of those atoms escape. So when Jupiter forms from those blocks of ice, you need more ice to carry in the same amount of material. So the abundance of the ice as it forms and makes Jupiter, the abundance of water you find in Jupiter, all that other stuff, depends on, did it form from blocks of ice that were kind of warm or blocks of ice that were kind of cold? There's lots of other complications to take into account. You have to think about the size of those chunks of ice. You have to think about whether the gas, how much ice it took to have enough mass to pull the gas in. You have to think about how fast all of this happened. But the different models of how did Jupiter form all make some kind of prediction about how much water we should find in Jupiter. So it's a really key number to understanding how the planet formed. Does that help?
That sounds really good. I'm going to take over because there were some audio problems there. I have a question from Andy Sherwood, and she wants to know if there's a plan B if the rockets don't fire on 4th of July.
Well, there's a plan B, C, D, E, and F, but the basic idea is the main engine has to fire within a pretty short time window because it doesn't help any to slow down when you've already gone past Jupiter, and it doesn't help any to slow down before you get there. You really have to slow down at just the right time. Also, it's so far away that it's too late to send any commands. It takes almost an hour for the radio signal to get from the Earth to Jupiter. So by the time we even know what happened, it's all over. So that sounds like you got one shot and that's all there is. And that's sort of true. And we call it a critical event for that reason. It has to work and it has to work at the right time. However, the sequence of commands we put on the spacecraft is set up so that if the main engine fails for some reason, it will reboot things and try again. And we think we can get through a good 6 attempts to retry before it's too late and the spacecraft has gone by. So plan B is try again. And we have a sequence of commands on the spacecraft, which we have just tested to death, right? We've done everything we can think of to test, will the spacecraft really do this? And what all the things we can think of that could go wrong. And if they go wrong, what will it do to try and get the engine started again? We build all of that in. We turn off everything that doesn't have to be on, so there's no extra complications to cause a problem we haven't thought of. And if the spacecraft has a problem, we're pretty confident it will it'll follow its process and fire the main engine and get us into orbit. If we're not in exactly the right orbit, well, we can wait till it comes around to the planet again and adjust it. We don't have infinite capability to do that, so we have lots of scenarios, plan C, D, whatever, of, all right, suppose we don't get the main engine burn all the way, but we get into some orbit, what would we do to adjust it to try to still do our science mission? So we have lots of thoughts about that. We have the part I don't want to think about if it fails so completely that it goes past the planet. When would we give up and start at least look at Jupiter as we fly by and see if we can do something with that? And the main thing that gives us confidence is, in addition to all of this planning and all of this testing, this is going to be the 3rd time we fired the main engine. We did those deep space maneuvers to aim to get back to Earth. They were similar kinds of rocket burns to the one we're doing at Jupiter. They weren't critical. They didn't have to happen at exactly the right time, but they all worked flawlessly. So we're pretty confident that it's all going to work. And, I'll only be crossing my fingers and, biting my fingernails a little on the 4th of July.
That's great. Let's see. William Merman asks, are there any challenges with the spinner craft? Is maneuvering more difficult that way?
So there's some big advantages and there's some challenges too. The challenge is that you don't have the same kind of control over where you point things, right? Because it's going to constantly be spinning. And what you really control is how fast you spin and the direction of the spin axis. But we're designed to handle that. Our instruments are designed, in fact, to take advantage of that spin and sweep out a circle on the sky, and they're all designed to want it to be spinning. So that part's okay. And the fact that we have to spend some fuel in order to change the direction of the spin axis, that affects how much fuel we need to carry, but it's not the biggest factor. It's not as big as those main engine burns and the fact that we have to tweak our orbit once we're in Jupiter. The biggest thing I would say that's a drawback to the spinner is that we have a lot of experience with 3-axis stabilized spacecraft, and Lockheed Martin has built lots of spacecraft like this before that were not spinners. So we had to go over everything and make sure there wasn't some hidden assumption that had worked great for all the previous spacecraft because they were not spinners and this one is. Haven't found any problems like that. People have, taken care of things. In general, it's all working, but that's, got to be a little tiny worry in the back of your mind if you want to be properly paranoid to make this whole thing work.
That's great. Let's see, we've got one from Babette from Star Creek Astronomical Society. She said, did you have to modify the electronics in the instruments in order to help them survive the radiation?
Yeah, I forgot to mention this. So that's really one of the innovations on our spacecraft is rather than modify all the electronics to handle the radiation belts at Jupiter, the main thing we did is we put them all inside a giant titanium box. So we are carrying the equivalent of an armored tank all the way out to Jupiter, this hundreds of kilograms box of titanium, which we call the radiation vault. And then we crammed all the electronics that we could inside the radiation vault. So that way we were able to use heritage electronics that was similar to stuff we've flown before, and the radiation environment for the stuff inside the vault isn't much different from what we've flown on other spacecraft. There's some exceptions to that. There's some extra details. There's some things that can't be inside the vault, like the solar panels. So we had to do stuff to handle the radiation environment, and we pay attention to the radiation. But the biggest thing we did was just carry this huge box all the way to Jupiter.
All right, I think we've just got time for a couple more. Let's see, Mark Jones is asking, here there have been some recent impacts into Jupiter's clouds. How can Juno observe and help us learn more from these?
Short answer to that, I don't know. I finally got to answer, I don't know. The reason I don't know is we got to think here about timing, right? An impact on the clouds of Jupiter, if we don't look at it till a month later, we may not learn anything about that impact. It may all be swallowed up and gone by then. And we also have to think about how the dynamics of the atmosphere work, because we get each pass of Jupiter on a different longitude. So if you're interested in something where you have to observe a particular longitude, we've got to figure out when that longitude is going to come around and the motions of the jet streams for how it will carry whatever it was that we were interested in around the planet. So we need to know what longitude it's going to be at the time we're going to match up with it. So I'm sure that if an impact happens in just the right time and place, we'll learn something about it. But anything that happened, recently, and then I say, in August when our spacecraft turns the instruments on, because, we get into orbit, we don't turn the science instruments on until after we're in orbit. The observations we do then may or may not tie up to something that somebody saw last week.
Right, that makes sense. Okay, we have a quick follow-up to the radiation question from Stuart Myers. He wants to know, wouldn't lead be more effective than titanium?
I want to be careful here. The short answer is no. The longer answer is choice of which materials you use and which combinations of materials you use is a technical decision. And the United States has rules about explaining how to do radiation shielding in a public forum. So even if I knew enough to tell you all the details of why you should choose which materials, I'm probably not allowed to.
That's a great place to end then. I'm going to hand it over to Brian. Let's see, maybe, Stephen, if we could mute both of us and see if he can do a couple of closing moments here. Thank you so much. That was really, really fantastic.
That was great.
Good. I had fun. All right, I'll put it on mute until somebody tells me otherwise or the connection disappears.
So we're going to hope that we don't have any extra feedback here. Well, that's all for tonight. You can find this telecon along with many others on the Night Sky Network under the Outreach Resources section. Just search for webinar. We will post tonight's presentation along with the other ones on the Night Sky Network YouTube channel by the end of the week. You can also find other resources and Jupiter-inspired activities on this webinar's dedicated resource page. And now for our raffle. So Vivian's going to count and determine this month's winner of the ASP's